Have you ever paused and wondered where it all came from? The oceans, the rain, the water flowing quietly through you. None of it should exist on a young, fiery Earth. Tonight, we're following the trail of every drop, from the birth of a molten planet to the ice that traveled across the stars. Because behind every wave and raindrop lies a quiet miracle, the universe learning to flow and to keep flowing against all odds. Now, take a slow breath. Let your eyes grow heavy and your curiosity drift. Together, let's follow the water back to where it all began.
Chapter 1. A Dry Beginning. Imagine standing on a planet that's still cooling from birth. Not the gentle blue world we live on now, but a place where the horizon glows and the ground underfoot isn't rock so much as a roiling, incandescent sea. That was Earth in its earliest days, a molten, violent furnace. The first thing to understand is how thoroughly inhospitable that environment was. If you tried to pour a glass of water on the surface back then, it wouldn't ripple or clink. It would vaporize instantly, hissing into the sulfur and carbon-rich sky. This was the Hadean, roughly 4.5 billion years ago, when gravitational energy, relentless bombardment by planetesimals, and the decay of short-lived radioactive elements kept Earth's surface temperatures far hotter than anything humans have experienced. Picture a world where impacts were common and colossal. One of those collisions was so energetic it likely blasted off enough material to form the moon. Each strike didn't just leave a crater. It injected so much heat that large swaths of the planet briefly melted, creating what scientists call a global magma ocean. For a long stretch of time, the surface was a mantle of liquid rock, and any volatile compounds, those substances like water that can be vaporized, couldn't settle down on the surface in liquid form. Now think about the sky. It wasn't the nitrogen-oxygen mix we're used to. It was thick with carbon dioxide, nitrogen, methane, ammonia, and sulfur gases stripped from the materials that built the planet and churned out by continuous volcanism. Water was present, yes, but as steam, an invisible, high-energy fog. The pressure and temperature were such that water couldn't collect into lakes or seas. Even if pockets of cooler conditions existed, any surface water would be quickly boiled away or photodissociated by intense ultraviolet radiation from the young sun and chemical reactions in the atmosphere. That sounds bleak, and it was. But here's the twist that makes our ocean story possible. The raw materials for water didn't need to be on the surface. They were hiding in plain sight, locked inside the very stuff that made up Earth. When you look at a rock today, it can feel solid and permanent, but deep inside those minerals, at the atomic scale, there are places where hydrogen and oxygen can be stored. During the planet-forming collisions and the era of the magma ocean, many volatile elements didn't escape into space entirely. Some were incorporated into newly formed minerals, trapped as hydroxyl groups, or dissolved into molten silicate. Even more intriguingly, when iron separated to form the core, it didn't do so as a dry, perfect metal. Molten metal can absorb light elements, including hydrogen, so some of Earth's hydrogen could have been sequestered into the core during differentiation. Imagine putting sugar into hot tea. It dissolves and disappears from sight, but it's still there, mixed in, waiting. There's a helpful everyday analogy. Think about putting an ice cube in a roaring fireplace. On the hearth, you don't expect a puddle. The heat destroys it. But if that ice gets trapped in a crack in the mantle or hidden inside a loaf cooling in the next room, it can survive the heat, protected until the environment changes. Similarly, bits of water survive the Hadean not as oceans, but as chemical bonds or dissolved atoms in the rocky and metallic parts of the planet. This hidden reservoir made all the difference. As the planet cooled, as volcanic activity continued, and as smaller, water-rich bodies crashed into Earth later on, those trapped volatiles were gradually released back into the surface environment. Minerals can break down, melted rock can degas, and impacts can vaporize and redistribute material. Processes that slowly turned Earth from a dry, blistering world into one where liquid water could persist. It wasn't a single event, but a long, messy process of release and retention. Make this personal for a moment. Imagine packing your belongings for a long trip, but you can't carry liquids. They'll spill. So instead, you tuck the liquid into absorbent cloths and tightly sealed containers. Years later, when you reach a safe place, you squeeze those cloths and open the containers and the water comes out. Earth did something like that on a planetary scale. It hid its liquids where they wouldn't be lost to the heat, then, over millions of years, let them out when conditions allowed. That early tension between a surface too hot for water and interiors that quietly stored it is central to how our planet became habitable. The surface dryness didn't mean there was a permanent absence of the ingredients for life. It was a storage problem solved by time and cooling. Without that hidden inventory, subsequent processes like late impacts and volcanic degassing might not have had anything left to release, and our blue oceans would have remained only a dream. So when you look at the sea next time, remember, it has a past that began not with gentle rain on a cool world, but with magma, fire, and a planet that learned to keep its water safe until the right moment. That buried inventory set the stage for the slow, miraculous transformation from a dry, hostile place to the watery cradle that eventually allowed life to arise. Chapter 2. The Hidden Water Within Rock. Think about holding a rock in your hand. It feels solid, heavy, unyielding, the opposite of what we usually think of as wet. But down in Earth's early crust and mantle, those hard, dry-looking rocks were quietly keeping something vital inside: hydrogen and oxygen atoms, tucked into their crystal structures like secret letters folded into an old book. That hidden water wasn't a puddle or a lake. It was chemically bound, trapped at the atomic level inside minerals. To understand how the oceans began, we have to learn how that invisible water escaped. Imagine minerals as tiny cages made of silica and iron and magnesium. Within those cages, hydrogen atoms can sit as OH groups, and oxygen atoms are part of the larger lattice. Minerals like olivine, pyroxene, and amphiboly can host these hydroxyl units. In some places, entire minerals form that include water. Think of hydrous minerals such as serpentine or talc. If you could zoom in, you'd see what looks like water built into the scaffolding itself. It's not liquid, but it's there, waiting. Now picture the early Earth. The crust was thin and unstable, and the mantle convected like a slow-moving pot of lava. Tectonic movements and heat brought those hydrous minerals up toward the surface. When volcanic eruptions ripped open the ground, they didn't just spray molten rock. They tore those mineral cages apart. The heat broke chemical bonds, and the freed hydrogen and oxygen atoms met. In the violent furnace of a volcano's throat, they paired up as steam. Think about the last time you opened a hot oven. The blast of steam that hits you is sudden and unmistakable. Early volcanic eruptions were like that, but on a planetary scale and far, far more frequent. Each time a volcano erupted, it injected pockets of steam and other gases into the sky. Over millions of years, these eruptions were not rare events, but constant whispers. Eruptions day after day, century after century, each one adding a little more vapor to the atmosphere. It's easy to imagine this as a slow drip that becomes a flood. The collective effect of billions of tons of rock releasing bound water is staggering. Outgassing, the process by which the Earth's interior vents gases, built up the early atmosphere piece by piece. Carbon dioxide, nitrogen, sulfur compounds, and crucially, water vapor accumulated. At first, the steam hung in a thick, opaque haze, making the sky look like a boiling kettle. If you could have stood on that surface, and you can't, but let's pretend, you'd find the air heavy with moisture, the horizon blurred by vapor, the land steamed and shrouded. There's another piece people sometimes miss. Not all the water came from the mantle alone. When the early crust formed, impacts from icy planetesimals and comets also delivered volatiles. And subduction, the process where one crustal plate dives beneath another, recycled surface water back into the mantle. But even that recycled water could become trapped in new minerals and later released by volcanism. So the mantle and crust were both sink and source, a dynamic reservoir that regulated the amount of water the planet could hold on its surface. Making this personal, think of a sponge soaked under the faucet, then wrung out. The sponge is the rock. Heating and pressure are the hands squeezing it. The water that comes out is the steam and vapor. The rock retains some moisture, but the wringing keeps going as long as energy, heat from the interior, is supplied. Early Earth never ran out of energy, so outgassing continued over geologic timescales. Eventually, the planet cooled enough that the steam began to condense. Clouds formed, rain fell, and the first bodies of liquid water pooled in low places. But those first drops didn't fall from some watery sky from day one. They were the end product of a long chain. Atoms locked in crystals, liberated by heat, mixed into the atmosphere by eruptions, and finally condensed as temperatures allowed. Every ocean drop can be traced back to that moment of liberation deep within the rock. There's a subtle, humbling lesson in this. Water on Earth isn't just something that arrives from the outside. It's also something that Earth itself makes available through its inner workings. The planet's geology and its hydrology are not separate stories. They're chapters of the same book. When you drink a glass of water, you're tasting a history that includes violent volcanism, chemical bonds breaking, and the slow, patient convecting of mantle rock. And the story continues even now. Modern volcanoes still release steam and gases. Subduction zones still ferry water deep into the mantle where it can be locked away again or released later. Our oceans are partly a memory of those ancient eruptions and partly an ongoing conversation between Earth's interior and its surface. So next time you stand by the sea or watch steam rise from a kettle, remember, some of that water once lived inside a rock,
held captive until the planet's own heat let it go. Chapter 3. The Planet That Reigned for Centuries. The planet that reigned for centuries was not a gentle, familiar drizzle. Picture instead an angry sky, a relentless percussion of water and sound that didn't let the land sleep. When the last of the incandescent rock finally cooled enough for steam to stop roaring off the surface, that vapor had nowhere to go but down. Clouds thickened like swelling bruises across the sky. Thunder rolled with an almost constant cadence, and the first true downpour in Earth's history began. And it didn't stop for what, to us, would feel like forever. Imagine standing there, not with a spacesuit, but just in your mind, feeling the first droplets strike a crust that had known only fire. Each drop would have been a tiny hammer, cool and sharp against an otherwise blistering world. At first, the rain probably hissed when it hit molten pockets and sizzling vents, steam rising again into the already saturated air. But gradually the surface darkened, steam thinned, and the water began to accumulate. Rivers that had never existed before started to draw lines across the land, not as gentle streams, but as powerful, sediment-packed flows. Those flows carved valleys with a patient, inexorable force. They chewed away at rock, carried grit and dust across hundreds of miles, and deposited layers that would one day be read like pages in a history book. You can relate to that on a small scale. Think about the last time you watched heavy rain transform a familiar street. Gutters overflow, the sound is almost hypnotic, and the world smells green and cleansed. Now multiply that by 1,000,000, over years, centuries, millennia, and replace asphalt with granite and basalt. That's the scale we're talking about. The rain didn't just wet the surface, it reshaped it. Low spots became basins, basins filled, and what started as puddles coalesced into lakes, seas, and ultimately oceans. The pale blackened ball that had been Earth slowly brightened as liquid covered its face, turning it into the shimmering blue jewel we recognize today. There were different actors in this drama. Some of the water came from inside the planet. As the molten mantle degassed, huge amounts of water vapor and carbon dioxide were expelled into the atmosphere. Other water likely arrived from space, icy comets and asteroids that slammed into the young planet, delivering frozen cargo. Either way, the sky was heavy with vapor. For a long time, the surface couldn't cool enough to let all that vapor condense. But once it did, the clouds became enormous engines of precipitation. Thunderstorms rolled across the globe with an intensity that dwarfs anything we experience now. Lightning would have been frequent, bathing the landscape in brief, violent daylight, perhaps catalyzing the chemical reactions that later made life possible. The rain's effects were both destructive and creative. Erosion tore down mountains and smoothed rough edges, but it also created the sedimentary layers where we later find fossils and clues to early conditions. Chemical weathering, the process where water reacts with minerals, started to change the composition of the crust and the atmosphere. Dissolved ions ran off into basins and oceans, setting the stage for the complex chemistry of life. It's a bit like watching a messy kitchen after someone has cooked a feast. Chaos at first, but the ingredients are now mixed, ready for something new to emerge. And there was persistence to this weather. The script of those first rains was not a short scene, but a long, slow act. Rain that lasts centuries
may sound like a metaphor until you imagine how that kind of persistence would amplify its effects. Every downpour widened channels, every flood deposited more sediment, every storm redistributed heat and chemistry in the atmosphere. Over geological time, what starts as a trickle becomes a river becomes a sea, and a sea becomes a stabilizing climate regulator, reflecting sunlight and hosting the chemistry of life. There's something deeply personal about this transformation. We all know the small comforts water brings. A hot shower, the relief when a summer thunderstorm cools a sticky evening, the way rain can wash away the dust of a long day. But on the early Earth, water did more than comfort. It reshaped the very canvas of existence. The same element that dampens your hair and soaks your shoes was the sculptor that cut continents into shapes, the blanket that tempered an angry planet, and the solvent that mixed the world into a chemistry lab large enough for life to spark. Even now, when you look at a photo of Earth from space, that vivid blue and white marble, you're seeing the long-term result of that relentless precipitation. The rain that carved valleys and filled basins gave our planet its color and its habitability. It created coastlines where ecosystems could eventually flourish, shallow seas where sunlight could meet nutrients, and a hydrological cycle that continues to recycle water between sky and surface. But the rain didn't simply stop once oceans formed. It evolved into the rhythms we're familiar with. Seasons, monsoons, storms, shaped by an atmosphere cooled and stabilized by a growing ocean. Those rhythms would, in turn, influence where life could gain a foothold. The long, wet chapter of Earth's youth laid down the physical and chemical groundwork. In other words, the storm that seemed endless to that world was actually a patient craftsman, smoothing rough edges, filling hollows, and creating niches. So when you next feel the rain on your face, when you stand under a sky that lets loose and listen to distant thunder, there's a quiet connection to that ancient deluge. The water touching your skin is part of a lineage that once fell ceaselessly, reshaping a wild, newly formed planet into a home. Those centuries of rain were not merely weather. They were the transition from a world of fire to a world of water, the moment the planet took its first deep inhalation of life's potential. As the downpour finally gave way to steadier climates and calmer seas, the stage was set for something even stranger and more consequential. The carved valleys and filled basins weren't just scenery. They were the laboratories, the pools, and the shores where chemistry could take a step toward biology. Next, we'll look at how those wet landscapes became the cradle for the first whispers of life. Chapter 4: The Cosmic Ice Messengers. But Earth didn't have to rely only on its own plumbing. Out in the dark regions of the young solar system were icy bodies, comets from the outer Kuiper belt and Oort cloud, and water-rich asteroids closer in that became unwitting couriers of H2O. Picture them as cosmic thermoses, carrying frozen parcels of water and organic material from faraway neighborhoods. Now imagine some of those thermoses lost control and smashed into Earth. The consequences were dramatic. Ice that had sat unbothered for millions of years suddenly met molten rock and fire, and a lot of it turned into vapor and liquid that could join the planet's growing reservoirs. Let's make this concrete. Comets are mostly ice and dust. Think dirty snowballs minding their own business until a gravitational nudge, maybe from a passing planet, sends them barreling inward. Asteroids,
especially the carbon-rich ones we call carbonaceous chondrites, aren't frozen solid the way comets are, but many of them contain hydrated minerals and bound water. When either type of object collides with Earth at tens of kilometers per second, the kinetic energy is converted into heat. That instant of violence is enough to melt and vaporize substantial chunks of their icy interiors. Some of that water escapes into space, but a surprising amount can survive the blast and be incorporated into the atmosphere, oceans, or crust. This is where the image becomes intimate. Think about holding a snowball and tossing it into a campfire. The outer layer sizzles off as steam, while some slush runs down into the coals, disappearing into the soil. On a planetary scale, those melted slushes were tiny, repeated events, but billions of them happened over geologic time. Each impact was like someone dropping a bottle of water into Earth's cup. At first it's a drip, then a trickle, and eventually a pour. Over millions of years, those drips and pours add up. We have scientific clues that these messengers actually delivered water. Meteorites that land on Earth, especially certain primitive types, contain hydrated minerals and water whose isotopic signature, ratios of heavy hydrogen, deuterium, to ordinary hydrogen, looks a lot like Earth's oceans. That's a fingerprint. For a long time, the debate centered on whether comets or asteroids supplied most of Earth's water. Classic measurements of some comets showed a deuterium ratio quite different from Earth's, which pushed many researchers toward asteroids as the main source. But the story isn't that simple. Recent missions have changed the picture. Spacecraft like Rosetta, which orbited Comet 67P, and sample return missions such as Japan's Hayabusa 2, Ryugu, and NASA's OSIRIS-REx, Bennu, have given us direct looks at these bodies. Rosetta revealed a comet with a deuterium signature that didn't match Earth's oceans, but Hayabusa 2 and OSIRIS-REx found hydrated minerals on their asteroid targets and even primitive organics, reinforcing the idea that asteroids carried significant water. Stardust returned comet dust to Earth decades ago, and tiny portions of comet material now sit in labs where scientists can test them with extreme precision. More recently, observations of other comets have shown a wider variety of deuterium ratios than previously thought, some closer to Earth's, so comets can't be dismissed entirely. The takeaway is that the early solar system was messy and diverse. Water likely came from multiple sources. Timing matters. In the first few 100 million years after the sun lit up, the inner solar system was crowded with leftover planet-building debris. There were epochs of higher impact rates. One famous episode, often called the Late Heavy Bombardment, that could have delivered a lot of extraterrestrial material in a geologically short time. Each wave of impacts had the potential to shift Earth's surface conditions. Imagine your house sitting in a drizzle for a few hours versus a steady rain for days. The latter is when puddles form and water starts pooling in low spots. Likewise, a sustained influx of icy bodies could have pushed surface reservoirs past a tipping point where liquid water became stable and widespread. We also need to consider how much of the incoming water actually stayed on Earth. Big impacts are two-edged swords. They bring water, but the shock can vaporize surface water and fling material into space, potentially erasing some gains. Yet models and experiments suggest that a sizable fraction of water from moderately sized impacts is retained, captured by the cooling atmosphere or by being trapped in newly formed minerals. Over time, as the planet cooled and an atmosphere thickened, Retention improved, making later deliveries even more effective. There's something very human about this cosmic handoff. When you pour water into a glass, you're making a small but real change. When the same happens on geological scales, the result can be the difference between a dusty-tinged landscape and one full of rivers, lakes, and eventually life. Consider that many of the molecules in the water you drink may have originated in the cold outskirts of the solar system, hitching a ride on a meteor or comet long before there were humans to notice. That's a powerful way to feel connected to those ancient events. The same H2O that melted after an impact might now be running through a stream where you caught your first fish, or boiling in a kettle in your kitchen. One more humanizing detail. Those cosmic deliveries didn't just carry water. They brought organic molecules, amino acid precursors, simple carbon compounds, which could have helped seed the chemistry that led to life. So the ice messengers were, in a sense, delivering both the solvent, water, and some of the building blocks for the chemistry living systems rely on. It's like receiving a package that contains both cooking oil and flour. Each is useful on its own, but together they let you do more. So how confident are scientists that these icy visitors were decisive? Pretty confident that they played a major role, although the exact split between cometary and asteroidal contributions is still debated. The consensus is that Earth's water is the result of multiple processes. Internal degassing supplied some, and external deliveries supplied more. Those cosmic ice messengers were probably the nudge that tipped a damp planet into a wet one. The final pours into a cup already half full, turning trickles into streams and pools into oceans. Think of your shower turning on for the first time in a dry house. The pipes, the water heater, the roof, they all had to be in place. But without that initial faucet, those deliveries of water, the transformation wouldn't have been possible. The icy bodies that struck ancient Earth were that faucet. Their melted hearts and frozen cargo helped fill the basins that became rivers and seas, and in doing so, set the stage for everything that followed, up to us sitting here, wanting to understand our own origins. Chapter 5. The Asteroid Belt Connection. If you close your eyes and imagine where the water on Earth came from, you might picture comets, the icy, cinematic snowballs that streak across the sky. For decades, that was the dominant image. But recent isotope detective work has turned that picture on its head, and the real culprits might be a lot less glamorous. Small, dark rocks that have been quietly drifting between Mars and Jupiter for 4.5 billion years. Here's the setup. Water isn't just H2O you can see, it has a fingerprint. Each hydrogen atom can be the ordinary kind, or the heavier isotope called deuterium. The ratio between deuterium and normal hydrogen, we call it DH, acts like a barcode that tells scientists where a particular drop of water came from. When researchers measure the DH ratio in Earth's oceans and compare it to various objects in the solar system, patterns emerge. Comets sometimes match, but many do not. That's where carbonaceous chondrites, a class of ancient asteroids, become interesting. Carbonaceous chondrites are primitive, chemically rich space rocks. They're not flashy like a comet's icy tail. They're dark, crumbly, and easily overlooked. But that's exactly their strength. These meteorites are like unopened time capsules from the early solar system, preserving the chemistry of the region where they formed. When scientists started measuring hydrogen isotopes, oxygen isotopes, and other elements in water-bearing minerals inside these meteorites, something remarkable happened. The isotopic fingerprints lined up with our oceans almost perfectly.
Think about that for a second. The water you drink, the salt water that brushes your toes at the beach, the fresh water in lakes and rivers, a substantial portion of it may trace back to countless tiny asteroids that drifted inward from the outer asteroid belt. These objects, called carbonaceous chondrites, formed in the colder, more distant neighborhoods of the early solar system where volatile compounds like water ice and organic molecules could survive. Over time, collisions nudged some of them inward. When they slammed into the young Earth, they delivered their cargo. There's a human side to this science that I find quietly profound. Picture a scientist hunched over a mass spectrometer late at night, carefully analyzing a speck of mineral smaller than a grain of sand, hunting for that subtle deuterium signal. Or imagine a meteorite sitting on a garage shelf. It looks like just a rock, but to someone who knows its history, it's evidence that the story of life's essential ingredient is written in tiny, ordinary things. Those images make the discovery feel intimate, the stuff of everyday life shifted into Earth's narrative by random violent acts in space. The match between carbonaceous chondrites and Earth isn't absolute, it's nuanced. Not every meteorite has the same isotopic mix, and the asteroid belt itself is a diverse place. But the more samples we collect and analyze, the clearer the trend becomes. The chemistry of these stones, not only hydrogen isotopes, but also oxygen and certain organic compounds, tracks tightly with seawater. That's a stronger case than one-off comet matches, which often show much higher deuterium levels than Earth's oceans. Another point that makes this idea believable is timing. Planetary scientists reconstruct a chaotic early solar system, planetesimals forming, migrating, and colliding. Giant planets shifting positions and stirring the small bodies into new orbits. During those volatile epochs, shipments of water-rich material could plausibly be sent inward where Earth could intercept them. This model doesn't require a single massive delivery. It could be a steady trickle or a series of impacts over millions of years. Either way, those dark asteroids become the quiet architects of our seas. There's also a poetic twist. Carbonaceous chondrites don't just carry water. They bring along organic molecules, amino acids, and other prebiotic chemicals. The Murchison meteorite, for example, stunned scientists when they found a suite of complex organics preserved inside it. If water and organics arrive together, the stage for life becomes more understandable. It would turn planet formation from a sterile assembly line into a delivery service that supplies the raw materials for chemistry to take a life-friendly turn. Why does this matter for you on a personal level? Because it changes how we think about our place in the cosmos. When you sip a glass of water or watch a sunset over the ocean, you're not just witnessing a local phenomenon. You're holding the aftermath of ancient, solar system-wide processes. The idea that tiny, overlooked rocks from the asteroid belt helped make Earth habitable gives an everyday object, a drop of water, a dramatic backstory. It's a reminder that big outcomes can come from small, cumulative events. This realization also shifts how we search for life elsewhere. If asteroids can seed planets with water and organics, then rocky worlds and other systems that experience similar bombardments might have a head start. It broadens the concept of habitability beyond planets that form exactly like Earth to include those that receive extra deliveries of life-friendly ingredients. That's why missions that visit asteroids and return samples are so valuable. They're not just about cataloging rocks. They're about testing hypotheses on how water and life's precursors move around planetary systems. So next time you stand by the water, think about the journey those molecules made. From icy mantles around dust grains in the distant reaches between Mars and Jupiter, to violent collisions and slow gravitational nudges, to a final resting place in the blue expanse that covers our planet. It's a story that connects the small and the vast. Carbonaceous chondrites may not have the spectacle of comets, but they have something even more compelling, a quiet consistency that fits the chemistry of our oceans and possibly the chemistry of life itself. That quietness is part of the wonder. The universe's most ordinary travelers might have done something extraordinary for us. Chapter 6. The volcanoes that breathed oceans. Even as icy rocks fell from space, something else on Earth was quietly and violently doing its part. Deep beneath the young crust, the planet was alive. Molten rock simmering, plates shifting, pressure building until the ground ruptured and the world exhaled. Each volcanic eruption was not just a spectacle of lava and ash. It was a puff from Earth's lungs, pushing up steam and gases that had been trapped for eons. Those blasts of hot vapor were the planet's way of saying, "I will hold on to the water." Picture it. Instead of a calm sky, imagine a horizon filled with towering plumes. They weren't only silica and incandescent rock. They were full of steam, carbon dioxide, nitrogen, sulfur compounds, the volatile ingredients that would remake the atmosphere. When magma rises and decompresses, dissolved gases come out of solution, like bubbles escaping a shaken bottle. On the early Earth, there was a lot more to bubble out. Water locked in minerals in deep reservoirs was liberated as vapor. The result was a steady, planetary exhalation that, over millions of years, made the air thicker and more capable of holding heat. Why does that matter? Because temperature and pressure control the state of water. If the air is thin and cold, water either freezes or escapes into space. But with a denser, gas-rich atmosphere, heat becomes easier to trap. Carbon dioxide and water vapor act as greenhouse gases. They slow the loss of infrared energy to space and keep surface temperatures high enough for liquid water to exist. So every volcanic plume that pumped out steam was effectively turning the thermostat up, allowing rain to fall and to remain liquid rather than immediately freezing or bouncing off a forever frozen surface. There's something profoundly intimate about this process. Think of Earth as both creator and caretaker. The planet's interior produced the raw material, steam and gases, and the atmosphere, thickened by that outgassing, allowed those steam clouds to cool and condense into rain. Those rains filled basins, carved channels, and stitched together the first rivers. The story isn't one of external generosity alone, it's also internal stewardship. Volcanism didn't merely deliver water to the surface. It also created the conditions that let water stay and cycle. That cycling is a key point. Once water started falling, the planet's geology kept working behind the scenes. Some of that surface water soaked into newly forming rocks or was carried down at convergent plate boundaries. Minerals trapped water in crystal structures. Sediments captured salts. the mantle swallowed portions of the ocean only to spit them back out later in later eruptions. Volcanoes and tectonics together formed a long-term plumbing system, a planetary recycling program that regulated how much water lived on the surface versus in the deep earth. In other words, Earth's breath wasn't a one-off sigh. It became a rhythmic, ongoing exchange between the surface and the interior. Relating this back to something you can feel today, modern volcanoes still release steam and gases in much the same way, just on a smaller scale relative to Earth's early fury. When you see footage of an eruption and notice the towering steam, that's the same process rewarmed and reenacted. We can measure the gases, water vapor, CO2, sulfur dioxide, and follow their influence on local weather and climate. In a very real sense, every volcanic plume is a reminder that the planet's internal chemistry remains linked to the water we swim in and the air we breathe. It's also humbling to think that the oceans you might have swum in, the rain you've stood under, the rivers you've kayaked, a portion of that water began as a puff of vapor from beneath the ground. When you look at the sea, you aren't just seeing melted ice or stolen cometary ice. You're seeing Earth's own outgassing cooled and collected. The image of our planet breathing oceans helps bring that deep time process into something personal. It's as if the ground beneath your feet exhaled slowly over millions of years until a blue edge pooled up and became home. There's a poetic justice to it. The very heat that made the surface hostile, molten interiors, erupting volcanoes, also made it hospitable by building an atmosphere. Too little volcanic activity, and Earth may have stayed thin and bitterly cold. Too much, and greenhouse gases could have boiled oceans away. The balance struck was precarious but perfect enough to let water persist, cycle, and ultimately support life. And because this is a story that continues, the planet didn't stop caring for its water once the oceans formed. Plate tectonics, weathering, and ongoing volcanism created feedbacks that helped stabilize climate across eons. Weathering of silicate rocks, for example, slowly removes carbon dioxide from the atmosphere and deposits it into the crust, which can later be recycled by subduction and returned to the air through volcanic activity. That long planetary heartbeat, exhale, capture, recycle, is why Earth has stayed wet when so many neighboring worlds did not. Imagine standing on an ancient shoreline, if even for a moment in your mind. You'd feel mist on your face and hear distant thunder, not from a storm alone, but from volcanic vents far inland or along a rift. That sensory overlap, steam smelling faintly of sulfur, clouds gathering, the steady drum of rain starting to patter, is where geology and climate converge. It's the same convergence that made lakes and tides possible, that paved the way for shallow pools to concentrate organic molecules, and that set the stage for life to take its first breath. So when we talk about oceans being breathed into existence, it's not just poetic. It's a description of a physical process where Earth's internal heat and chemistry literally produced and sustained the water cycle. The planet acted like a guardian, exhaling steam to thicken the air, and then using its tectonic machinery to keep that supply in balance. That interplay is one of the most intimate forms of planetary self-care, and it's the reason a wet, temperate world exists for us to explore, study, and ultimately call home. Next, we'll follow that water from its first raindrops into the landscapes it carved. How rivers, seas, and shorelines evolved from this volcanic breath into the dynamic habitats that would eventually host life. Chapter 7. The fragile balance that keeps water here. Think about the water in the glass beside you. A tiny universe of motion, molecules racing, evaporating, condensing, finding their way back to the liquid. Now stretch that image to a planetary scale, and you'll begin to grasp how precarious our supply really is. Water on Earth is not guaranteed. Left unchecked, sunlight, charged particles from the sun, and the cold of space would have slowly taken it away. Start with sunlight. Every day, sunlight warms the surface and teases water molecules upward. A hot morning can lift vapor from puddles, oceans, and soil into the air. That's the same basic physics that lets your laundry dry, only multiplied across oceans. Once in the upper atmosphere, that water isn't entirely safe. Ultraviolet light from the sun can split H2O into hydrogen and oxygen. Hydrogen atoms are tiny and fast. Some stick around a while, but others escape the pull of Earth and stream off into space. It's a leak you can't see, but it's happening now. Our planet exhales hydrogen, drop by drop, at a rate that adds up over geological time. Then there's the solar wind, a relentless gale of charged particles blowing outward from the sun. Left entirely unopposed, it can strip away a planet's atmosphere molecule by molecule. Mars is the cautionary example here. Smaller, colder, and lacking a strong magnetic shield, Mars had its atmosphere and water whittled away. Rivers and lakes that might have existed billions of years ago left behind dry riverbeds and the sad fingerprints of a world that could not hold on to its life-giving envelope. So, what stops Earth from following Mars's fate? Two big things: gravity and a magnetic field that wraps the planet in an invisible protective bubble. Gravity is the basic anchor. Earth is massive enough that most molecules of water vapor, oxygen, and nitrogen don't reach the escape velocity needed to leave. Even when individual hydrogen atoms are freed by ultraviolet light, not all get away. Many slow down, recombine, or get caught in chemical processes before they can vanish. The magnetic field does the heavy shielding. Created by the churning iron in Earth's outer core, our magnetosphere deflects charged particles from the sun, channeling them toward the poles where they create auroras instead of stripping the air away. Picture a kite in a gust. Without that tether, the air would take the fabric. Our magnetosphere is that tether, and it's quietly essential. If it weakened or flipped dramatically, the dance between the sun and our atmosphere would change, and the subtle losses of water could accelerate. But even with gravity and the magnetosphere, the balance is fragile. Earth is constantly losing a bit of water to space. Some vapor always makes it high enough and fast enough to be broken apart and lost. It's not catastrophic in a human lifetime, but over eons it matters. The planet is breathing, slowly, methodically, exhaling light hydrogen into the vacuum. Here's the twist. Earth also has ways of taking water back in, of replenishing what it loses. Volcanoes are one of the quiet replenishers. Deep within Earth, water is stored in minerals and in the mantle. When tectonic plates subduct, when one plate slides beneath another, water locked into oceanic crust gets dragged down into the mantle. In time, some of that water returns to the surface through volcanic outgassing. Every plume of steam from a volcanic vent is partly a geologic refund of water that once lived on the surface. The same processes that hide water in rocks can release it again in a slow recycling system that's been running for billions of years. Chemical reactions play a subtler role. Rocks react with water in ways that can either lock water in or release it. When certain minerals form, they incorporate water into their structure. Later, heat and pressure can break those minerals down, setting the water free. Even on the ocean floor, hydrothermal vents cycle water between the crust and the sea, moving dissolved minerals and reshaping chemistry in ways that keep the overall inventory of surface water surprisingly steady. What makes this all feel so delicate and so miraculous is how the rates of escape and replenishment are balanced without a central control. No cosmic engineer is checking the numbers. It's the result of planetary physics and chemistry finding a rhythm. Some vapor escapes into space. Some water is pulled into rock and recycled back up. The strength of the magnetic field waxes and wanes over geological timescales. Volcanism spikes and sags. And yet, through all that variability, the system has kept enough water in liquid form on the surface for life to evolve, persist, and thrive. Make it personal for a moment. When you step outside and feel the dampness in the air, or when you hear rain on your window, you're experiencing a process that spans deep time. The drop of rain that hits your sleeve might have been part of a volcanic plume a million years ago, trapped in mineral lattices, then returned to the sea and finally cycled through clouds to fall where you stand. Every time you drink a glass of water, you participate in that planetary inhale-exhale. That breath metaphor is apt because it conveys both fragility and continuity. Earth inhales when volcanic activity, chemical reactions, and plate tectonics bring water and gases back toward the surface. Earth exhales when sunlight and the sun's charged particles strip away the lightest components and when evaporation lofts moisture high enough for escape. It's a cycle paced in millions and billions of years, but it's a cycle you can sense in small ways every day. And it's worth noting that human activity nudges this balance too. We change atmospheric composition, slightly alter circulation patterns, and affect glaciers and ice sheets that hold enormous amounts of fresh water. While we are not about to strip the planet of its oceans anytime soon, our actions are part of the modern chapter in this ancient rhythm. We are, in a real sense, participants in Earth's breath. So when you think about water as an infinite, nonchalant backdrop to life, remember how contingent it all is. The oceans could have been lost, frozen, or sequestered. Instead, gravity keeps most of it close, and the magnetic field deflects the sun's attempts to steal it. Meanwhile, Earth's geology quietly pauses and releases water like a deep, slow lung. That fragile balance, the silent tug-of-war between loss and renewal, is what keeps rivers flowing, storms forming, and your glass refillable. It's not a permanent guarantee. It's a dance that's lasted billions of years, and we're living right in the middle of it. Chapter 8: Water and the Birth of Life. When the oceans finally covered the planet, something remarkable began. Imagine standing at the edge of a vast, calm sea. The same way we've stood on beaches, dipping our toes in and feeling the cool give of water. Now imagine that everywhere on Earth was that sea. Molecules, like tiny strangers at a crowded party, floated and bumped into each other. Some stuck together. Some drifted apart. Over time, A few of those sticky encounters made patterns that could copy themselves. That copying, the ability to make a like from a like, is the smallest, most rebellious definition of life. Think about what water does for you every day. It carries your coffee's warmth. It holds your favorite soup. It mends a scrape with a clean rinse. At a molecular level, water is doing something extraordinary. It's a solvent that doesn't just dissolve things, it organizes them. Its molecules are little magnets, positive at one end, negative at the other. Those charges let water glue other charged or polar molecules into neighborhoods where chemistry happens more easily. In those neighborhoods, under early Earth skies, chemistry found a language. There's another part to this story. Water moderates temperature. Oceans act like a slow, reliable thermostat. On a small scale, when you take a long bath, you notice the water stays warm. It doesn't swing from hot to cold the way a dry rock would. That thermal inertia meant early Earth seas held conditions steady enough for delicate molecular experiments to run longer. Reactions that needed time to build complexity were given that time. Without water's patience, molecules might have danced briefly and then dropped the beat. Surface tension and wetting behavior, those everyday things that let a water strider cruise across a pond or let a drop cling to a window, also matter. Tiny pockets and crevices in minerals, tidal pools that dried and refilled, layers of foam and surf all created microenvironments. These were places where molecules could be concentrated instead of being diluted into nothing. Imagine a puddle shrinking under the sun. Molecules that were once scattered are now packed together, more likely to interact. That cycle of wet and dry is a recurring theme in many origin of life ideas, because chemistry benefits from being both diluted and concentrated at different stages. We can make the story even more intimate by picturing the sea as a mirror that reflected the stars. Early Earth's calm oceans would have echoed the sky at night, a literal reflection and a metaphor for potential. In those reflective surfaces, light could drive reactions, splitting and recombining molecules. Ultraviolet light, intense in those days without an ozone shield, was both destructive and creative. It could tear bonds apart, but in doing so it created reactive fragments that recombined into new structures. It's a messy process, and life often starts messy. Another crucial player was the formation of boundaries, the first membranes. Lipid molecules, which have a water-loving head and a water-shy tail, spontaneously assemble in water into spheres or bilayers. If you've ever watched oil bead up on water, you've seen that preference in action. In the prebiotic soup, those lipids could self-organize into tiny bubbles that separated an inside from an outside. This separation is fundamental because it allowed a set of molecules to interact repeatedly with one another and evolve together, shielded from the vastness outside. Those protocells didn't need to be complex to be important. They just needed to hold chemistry long enough for useful patterns to emerge. Then came the miracle of replication. Some molecules, like certain strands of RNA, can both store information and catalyze reactions. In a world of lipid bubbles and fluctuating tides, RNA-like molecules could be brought together, helped along by mineral surfaces or ions dissolved in seawater, and in some cases copy parts of themselves. That's the spark, a pattern that makes more of itself. From there, selection, the bias toward what persists or makes more of itself, can begin. We still debate where exactly this happened. Some scientists point to deep-sea hydrothermal vents, warm, mineral-rich plumes where chemistry is vigorous and steady. Others prefer sunlit shallow pools that dried and refilled, forcing concentration and polymer formation through repeated cycles. Both options highlight water's role, but in different costumes. The vents as a slow, coaxing cook, and tidal pools as a high-energy workshop. Either way, the common denominator is water's chemistry and habit of creating niches. Making this personal again. When you rinse your hand under a faucet, you're watching one tiny act that mirrors the early ocean's generosity. Each droplet carries ions, molecules, surfaces, and the potential to change what's in it. That same generosity is what gave rise to the first membranes and the first molecules that could copy themselves. Life started not with a single triumphant moment, but with a million tiny acts of sticking and slipping, of dissolving and reassembling, happening across every tide pool and current. The image of the ocean as both mirror and womb captures the dual nature of water's gift. It reflected the broader universe, light, energy, and cosmic inputs, while providing a protected, nurturing chamber where fragile chemistry could grow into something persistent. From those early, wet experiments came the first cells. Small, imperfect, but persistent. They were the ancestors of every single living thing you know. The trees outside, the dog who greets you, and the microbes that live on your skin. So next time you stand at the shore or watch steam curl off a cup of tea, remember that water is more than life's backdrop. It's an active participant, a sculptor that shapes molecules into patterns that could replicate, a midwife that gave these patterns the space to be born. Without water's unique chemistry, none of us would be here to notice how lucky we are. And that quiet miracle, molecules learning to copy themselves inside tiny watery rooms, is the heartbeat behind every living story that followed. Chapter 9. The Endless Cycle. A planet that drinks itself. Look at the next raindrop that falls on your skin, on your window, on the pavement outside. It's ordinary, right? But ordinary isn't the right word. That single drop has a story that stretches farther back than your grandparents, farther back than the first cities, even farther back than the oceans as we know them. It has evaporated into the sky, condensed into a cloud, fallen as snow on a mountain, been frozen in an ice sheet for millennia, thawed and trickled into a stream, been sucked up through a plant's roots and released through tiny leaves as vapor. It has been part of a river and an ocean, a glacier and a mist, and at some point, maybe many times, part of you. This is the endless cycle. Earth drinking and spitting water back into itself over and over. The sun is the pump, heating oceans and lakes, pulling vapor up into the atmosphere. Gravity is the hand, tugging that vapor back down in the form of rain, sleet, or snow. Between those forces, water changes state, shape, and location. Evaporation, condensation, freezing, melting, runoff, infiltration, transpiration. The same handful of processes shuffle the same molecules around in an elegant, relentless loop. Think about your morning. You turn on the tap, and clear water fills your glass. You drink, and for a moment it's part of you, hydrating cells, carrying nutrients, cooling your body. Later, some evaporates off your skin, some leaves when you breathe.
some becomes part of your sweat. If you water a houseplant, the water will climb through its stems and leaves, and then return to the air again. If you flush the toilet, most of that water will join a treatment system. Some will seep into groundwater, and some will be recycled. Everywhere you go, you are participating in the planetary loop. Water's memory is long. A molecule in your bloodstream might have been in a Jurassic river or in the spray of a Cretaceous sea. The atoms that make up water are even older than that. Hydrogen in H2O was forged in the first minutes after the Big Bang. Oxygen was assembled in the hearts of stars. In that sense, nothing we call water is new. Today's rain is a reunion. Old molecules coming together in new forms, over and over. The timescales in this cycle vary wildly. A cloud's water might stay aloft for a few days. A mountain glacier can lock water away for thousands of years. Surface water in streams and rivers moves quickly. Groundwater can move inch by inch, taking centuries to travel. The ocean acts as the ultimate reservoir, holding a vast majority of the planet's water for very long periods. Those differences mean that when a drought hits or a glacier retreats, it's not just a local change, it's shifting where the planet stores its water and how long that water is taken out of the more immediate parts of the cycle. Because these pathways overlap with life, every living thing is both a passenger and a vessel for water. When a tree transpires, it pulls up water from the soil that was once rain. When animals drink, they incorporate water that may have been seawater in another epoch. Human bodies are about 60% water, and yet that water is not static. You consume, excrete, perspire, breathe. Your life is a noisy, intimate recycling plant, exchanging molecules with the world around you. The drop that slid down your face as a tear could have been ocean spray on a windswept shore decades ago. That's a humbling and slightly astonishing thought. This cyclical nature reshapes how we should think about scarcity and responsibility. On one hand, Earth never runs out of water in a literal sense. The same molecules will keep cycling. On the other hand, the distribution and timing of that water is everything. If groundwater is pumped faster than it's recharged, if glaciers melt faster than they can reform in winter, or if pollutants hitch a ride into the cycle, the quality, availability, and reliability of water shifts. The fact that water is endlessly recycled doesn't absolve us of impact. It just means our actions ripple through a system that connects polar ice to urban taps to desert oases. There's also a strange comfort in thinking of water as a connector. Imagine telling someone you love that some of the rain now hitting the pavement once swirled around a creature that lived millions of years before humans. Or picture holding a glass of water at sunset and realizing those same molecules might have been part of an ancient storm that carved a canyon. The cycle gives you a kind of kinship with place and time. It's a reminder that your day-to-day life is stitched into a timeline so broad you can't see its borders. Make it practical. The next time you hesitate to refill a bottle or to water a plant, remember why conservation matters. Small acts, catching rainwater for a garden, fixing a leaky faucet, choosing to use water thoughtfully, aren't about hoarding molecules that will never be replaced. They're about honoring the rhythm of a system that sustains and connects everything. They help keep water cleaner and ensure it's in the right places when communities and ecosystems most need it. If you want a visceral way to feel this cycle, stand in the rain with your face tilted up. Let your skin taste the sky. Close your eyes and imagine where that water has been. Mountains, oceans, clouds, deserts, forests. the mouths of rivers. It's a physical embrace with a process that has been happening since Earth found itself warm enough to hold liquid. You're not only witnessing the cycle, you're part of it. So when a storm passes and the world smells clean and new, don't just think of mud and wet pavement. Think of time folded into droplets. Think of atoms that have traveled light years in purpose and centuries in patience. Nothing truly disappears. It transforms and returns over and over in a planetary breath that has no beginning and no end. That's what it means to live on a planet that drinks itself, forever changing, forever the same at the molecular level and entirely alive in the way it sustains life. Chapter 10. The water inside you. Put your hand over your belly for a moment and feel the rise and fall. Inside that movement is a universe. The air you just breathed isn't just air, it's oxygen that was made in stars. The water moving through your body carries hydrogen that was forged in the first seconds after the Big Bang. When you swallow a glass of water, you're not only satisfying thirst, you're touching a kind of living history. You're tasting the memory of creation. Think about the last time you were really thirsty. Maybe you were running, or it was sweltering hot, or you'd been talking for hours. That first cool sip, how it hits the back of your throat, how the muscles relax, how sound and thought come back sharper, feels unremarkable. But each molecule of that water has a story that stretches back billions of years. The hydrogen in those H2O molecules existed before galaxies, before our sun, before the Earth itself. It was produced in the earliest moments of the universe. The oxygen? That was born in the heart of ancient stars, in nuclear furnaces that later exploded in supernovae, scattering their enriched guts across space. Those elements traveled, mixed into clouds of dust and gas, and eventually helped build our planet, and you. On a practical level, water is astonishingly ordinary. On a cosmic level, it's miraculous. Your body is mostly water, somewhere around 60% for an average adult, more for infants, less for elderly people. Your brain is about 3/4 water. Your blood around 90%. Those percentages aren't abstract numbers. They're the reason your thoughts stay crisp. Your joints glide smoothly. Your body regulates temperature. Every heartbeat pumps a sea of saline that carries oxygen, nutrients, hormones, tiny proteins, and the waste your cells need to get rid of. It's a circulatory ocean, and you are a ship navigating its currents. Because hydrogen is so light and abundant, it's been part of the cosmic material mix since the universe was nearly newborn. Oxygen, heavier and formed later, needed generations of stars to appear. So when you drink, you're combining elements with such different histories, one from the first minutes of time, one forged and hurled across the cosmos, that together make the simplest, most life-enabling molecule. It's a poetic mismatch. Ancient universal hydrogen bonding with star-born oxygen to become something that cools your tongue and helps your muscles move. Water in your body is also ancient in another sense. The molecules you breathe or sip have likely been through 1,000 forms. Rain that fell on dinosaurs, glacier melt pressed through bedrock, steam from volcanic vents, water cycles endlessly. There's a real possibility that some of the same molecules you have inside your cells today once flowed down a river that ran across a prehistoric continent. That continuity creates a strange intimacy with deep time. You are not only the result of genetic inheritance from your parents, you are an heir to an ongoing planetary procession of H2O,
Imagine a summer evening. You come home tired, fill a glass from the tap, and set your palm to the cold metal. Condensation beads on the outside, and you feel immediate relief when you drink. At that ordinary instant, your body accepts a chemical chorus composed of Big Bang hydrogen and stellar oxygen, plus a dash of minerals that leached out of rocks long after those stars died. The taste you notice, the faint metallic note from dissolved iron, the softness from calcium or magnesium, those are Earth's fingerprints on a cosmically ancient molecule. Drinking becomes a tiny ritual of remembrance. This also changes the way we think about waste and care. If the water inside you has been around through ages, the pollutants we introduce into the water cycle have a stubborn persistence. What you pour down the drain, what runoff carries into streams, what industrial processes release into rivers, they don't simply vanish. They join that ancient circulation and, in small or large ways, can come back to us. The water inside you is forgiving, but not endless. Treating it like a limitless resource is, in practice, disrespecting a relationship with a fragile system that took eons to assemble. There's a science to hydration that's useful and simple. Drink regularly, listen to your body, and remember that taste is also information. If your urine is consistently dark, or if you feel dizzy, those are signs your internal ocean needs topping up. But beyond the practical, there's an emotional and almost spiritual layer to this knowledge. When you pause and consider that the oxygen in your lungs came from vines and trees and stars, that the hydrogen came from the first breaths of the universe, it can be grounding. It places your personal needs within a vast story. Hunger or thirst stops being a private bother and becomes part of something much larger. So next time you pick up a bottle or reach for a glass, try this. Look at the water and imagine every element inside it traveling across time and space. Imagine atoms born in the furnace of a star or in the universe's first minute, now part of the tiny molecule that cools your mouth. Feel how your body responds as that history loosens its grip and becomes fuel, lubrication, memory. There's a humble, astonishing continuity here. The stuff that made galaxies and suns made you, and continues to make you every day with something as ordinary as a drink of water. You are, quite literally, made from the same elements that crossed space to shape this blue world. Chapter 11. The Future of Earth's Water. Think about the sound of a creek near your childhood home, or the way the ocean smelled the first time you stood with the wind at your back. Those memories feel permanent, like the water itself. But permanence is an illusion. The water that shaped those moments is the same water we share with billions of people in thousands of industries, and it's changing in ways that touch our daily lives. The climate is warming, and that changes everything about how water moves and lives on Earth. Warmer air holds more moisture, so storms can dump more rain in a shorter time. That's why places can flood one season and face drought the next. Glaciers and ice sheets, which for millennia acted like slow-moving reservoirs, are melting faster. When they shrink, rivers that communities have depended on through summer dwindle. If you've ever noticed a summer stream running lower than it did years ago, that's not just a seasonal fluctuation, it's a sign of a shifting system. At the same time, sea levels are rising. For people who grew up on coasts, that means familiar beaches are shrinking, and storm surges reach farther inland. For others, rising seas mean salt water creeping into wells that used to provide fresh, drinking water. Those impacts don't happen all at once. They accumulate. They show up as more frequent nuisance floods that disrupt commutes, as farmland too saline to grow crops, as entire neighborhoods having to adapt or relocate. Then there's the human side, our choices and habits. We've pumped groundwater faster than it can be replenished in many regions, lowering aquifers and causing land to sink. We've built dams that change river flows, cut off sediment that once built deltas and beaches, and changed ecosystems that filtered and stored water naturally. Pollution from industry and agriculture turns once clear rivers into health hazards. All of this reshuffles the ancient balance between land, sky, and sea. But it's not all doom and gloom. The future of water isn't pre-written. It's a set of possibilities based on choices we make now. Imagine cities where every roof is an opportunity to collect rain, where wastewater is treated and reused for irrigation, industry, or even drinking after proper purification. Picture coastal defenses that work with natural systems, restored wetlands and mangroves that absorb storm energy and provide habitats while also filtering water. These are not fantasies. They're being implemented in places around the world right now. Technology is part of the answer. Desalination plants have improved, becoming more energy efficient and less harmful to marine life, offering reliable fresh water where rainfall is scarce. Smart irrigation and precision agriculture can cut water use dramatically while maintaining yields. Remote sensing and sensors in rivers and aquifers give us data so planners can manage supplies more intelligently instead of reacting to crises. Yet technology alone won't fix inequity. Access to water is a social issue as much as it is technical. There are communities that already practice remarkable conservation and stewardship. Indigenous peoples, smallholder farmers, urban neighborhoods with creative sharing systems. Their knowledge needs to be honored and scaled, not replaced. And policies must ensure that water isn't treated merely as a commodity for profit, but as a shared resource tied to health, dignity, and survival. On a personal level, what we do matters. Fix a leaky faucet, yes, but also think bigger. Support local restoration projects. Vote for leaders who prioritize sustainable water management and climate action, and hold companies accountable for pollution and wasteful practices. If you garden, consider drought-resistant landscaping. If you live near a river or coast, get involved in citizen science programs that monitor water quality. These grassroots efforts often tip the scales in favor of protection. We'll also need to plan for hard choices. Some places may become less habitable without significant investment or relocation. That raises ethical questions about who pays for adaptation and who bears the burden of loss. International cooperation will be essential because water doesn't respect political borders. Rivers, aquifers, and atmospheric cycles are shared, and so must be the responsibility for stewardship. Most importantly, the story of water in the coming decades will be human. It's the farmer worried about a dry season, the child whose school has no clean drinking water, the coastal family watching the shoreline erode, and the scientist mapping groundwater levels. It's your choices in daily life and the policies we elect. There are failures ahead, certainly. There already have been. But there are also innovations, community victories, and policy wins that show another path is possible. If you ever feel small facing something as vast as Earth's water, remember that water itself is resilient and adaptable. It reshapes landscapes over millennia, finds new courses, seeps into new soils,
But resilience doesn't mean invulnerability. We can erode ecosystems and erode our own safety with short-sighted decisions. The line between sustainable coexistence and crisis is drawn by the priorities we set now. So how do we want this part of the story to read when it's passed down? Will it be a cautionary tale about lost rivers and submerged homes? Or will it be a story of communities coming together, of cities redesigned to work with nature, of technology guided by equity and wisdom? The answer isn't predetermined. Water will endure, but its story with us is still being written. If these quiet journeys help you relax, I'd love for you to subscribe and join us again. Tell me in the comments, where in the world are you watching from tonight? I read every message, and your place in this shared calm matters. Until next time, breathe slowly, listen to the sound of water, and remember, every drop has crossed the universe to be here, in this moment, with you. If a river, rain, or night ritual comforts you, share it below. I read every comment and cherish these stories, always.